Starch. I am the cognizant engineer at NASA's Jet Propulsion Laboratory overseeing F Prime, and I'm also the community manager that works with external partners, users, etc. with F Prime. First, I lament I was unable to be there in person, but I do appreciate this virtual meeting. If you have questions, please ask them. I would request that somebody in the room help repeat them towards the microphone because in earlier sessions I was having difficulty hearing some of the questions coming from the audience. So if you could just make sure that those are said into a microphone so I know what you're asking. Let's go ahead and begin. So first, let's talk a little bit about me. I'm your speaker today. I am a flight software engineer at the Jet Propulsion Laboratory. As I said, I'm the community manager of F Prime. My job is to oversee community development, work towards a better open source project, and interact with a lot of users like you. I've been an open source advocate for many years, and I was the downlink and tools lead for the Ingenuity Mars helicopter. Here's a picture of me during operations on that particular project. This will become relevant later on because Ingenuity will be our effectively a case study on how we used Linux in paired with F prime. So I just gave you a bit of a hint, but what are we going to talk about today? So first, we're going to go through just the basics. What is F prime? As we saw in the survey results, one person is using F prime. I'm pretty sure that was my response. Several of you are actually looking to use F prime, which I find very encouraging. If you have questions, reach out on our community. But the rest of you may not even know what F prime is. So we're going to go through a little bit about F prime. It's kind of the high level product slides. It doesn't get into a ton of technical detail, but it should give you a good overview. Then we're going to talk a little bit about F prime and Linux. That is where F prime and Linux have been paired for exactly what this workshop is about: space applications, safety applications. So we'll talk about the Ingenuity Mars helicopter, how it used Linux, and then to benefit everybody in the room, we have some lessons learned that we've pulled off the Ingenuity project. Excuse me, so that you can go away with some thoughts on how Linux was used in space and some of the lessons we learned from that activity. And then, time permitting, we will have questions. All right, so let's just begin with what is F prime? Well, F prime comes out of a world where the paradigm for space is shifting. As you can see in this graph, over the last 10 years, the number of things going into space on an annual basis has gone up substantially, both across the entire world and right here in the United States. So looking at this trend at JPL, we said, well, we can't continue to do the same old development patterns that we've done before, which were take one of the previous flagship missions, clone the software, own it, update it, and then ship it again. That's slow, it's expensive, and more importantly, at JPL, we were getting requests for doing a lot of smaller missions, CubeSats, etc., that didn't have the team size to be able to develop in that paradigm. So we started shifting and trying to come up with a new way of developing flight software. And that yielded the F Prime product line. So F Prime is a flight software product line that is the control software for your spacecraft, and it is designed to run on flight systems, uh, specifically CubeSats, small sats, that sort of thing. It can also run on flight instruments, flight deployables like the Mars helicopter, and we also support simulation and software technology development. So the goal here is you can develop technologies, research technologies in the same framework that you then ship to flight on a CubeSat or a Mars helicopter. Important to this conference is F Prime is open source. That means it's available to all of you today. It's available to anybody who might want to use it. And a lot of our project focuses on keeping that F Prime piece that is open available, supported, and useful to users. So what does F prime, well, how does F prime decompose? It is these four primary pieces. One, it's a software architecture. Our architecture is point to point, so we have modules, which we call components. We have ports, which represents the interface between a component and another component, and that all federates into what we call a topology, which is your system graph or your system topology, where all these components connect together to make the entire behavior of the system. That's the architecture. It is also the C++ framework, which comes with the C++ code that implements that architecture that we just talked about. It also comes with things like queues, threading, OS abstraction, etc. F prime also ships with a component library, which means some of those components that you use to construct your system are pre-canned. You can use them on your project if you'd like. They drop out in our tool creation scripts that create new projects so that you can quickly use all that F prime has to offer by adding your custom components to a standard set of existing components to quickly develop your application. And then finally, the tool suite. We have a number of tools, autocoders, build helpers, and a test GDS that all attach to the F prime ecosystem so that you can quickly get up and running with F prime with tool support. So that brings us to development. At JPL, we look at the software design process and development process for flight applications, as you see in this graph. You start with a design, then you do an implementation, followed up by unit testing, and then finally what we call integration testing. That is running system testing. You test on a hardware test bed or run the entire software application and test there. At each of these stages, design, implementation, unit test, and integration testing, we have built tools to support the developers. I like to say it is harder to violate or go around this process than it is to follow the process because the tools kind of guide you in the right path. That's one of the key pieces that I personally like about F prime is it makes this process easy. This process is one of those pieces that was heavyweight and expensive in the old days, and by adding automation and tools around each of these steps, we've made it faster. And then finally, F prime is flight proven. So we've flown on a number of missions. You can see a couple of them here. The Asteria CubeSat is the upper left. Ingenuity Mars Helicopter is the middle one. That's the one we'll be talking about in a minute. We have a couple of other CubeSats, NeoScout on the far right, Lunar Flashlight in the middle, and then a couple of missions that are in development. The one in the top that I haven't talked about is the Visar radar instrument, and the bottom right is the Cadre Federation of Rovers that is bound for the moon. So that's my quick overview of what F prime is. I'm happy to entertain a question or two if you have them. Otherwise, we'll dive into how F prime and Linux were used to make the Mars helicopter.
Yeah, one quick question.
Yeah, sure.
Do you have the ability for an application? Is there ability for a payload functionality to request things like disk space and features within the system?
Is there a feature for a payload to request disk space and other parts of the system?
Any resource. Yeah, resource. Yeah.
Yes. So we'll get into that in just a second. The first bit was more of kind of our general documentation. So on the subject of payloads, payloads are they're part of the F prime system, but they're not yet a first-class citizen. We're working on bringing a payload process into F prime to make it very easy to integrate payloads with existing F prime control software. Now, we do have an operating system abstraction layer that starts to speak to the resources in the system. So the system abstraction layer takes that features provided by the operating system, say file access or queue access, threading, that sort of thing, and provides it in a generic way up to F prime so that you can request these features without being hard tied to a specific operating system. That is actually the very next slide, so we'll get into more details there.
One last question.
Oh, yes, please.
Is F prime currently deployed in space?
Yes.
F prime is currently deployed in space, yes.
Really.
So it is still running on the Ingenuity Mars helicopter. Some of you may have heard that we've gone from a flight unit to more of a stationary payload, but it is still running on the surface of Mars. It just hasn't flown for over a year. All right, so let's talk a little bit about some of the technical details of F prime and Linux. So to start off with, the F prime software is this block that we see at the top of this diagram. It is the control software for your spacecraft. So it's kind of up to the project to say what they want it to do, what are the system requirements, etc. But F prime helps you architect that piece. F prime is built on an operating system abstraction layer that we ship, and then below the operating system abstraction layer are the types of operating systems we see. So I've put in there desktop Linux, some generic RTOS, could be VxWorks, could be FreeRTOS, and as we saw in Ingenuity, embedded Linux. Now, some of you may be asking, why include desktop Linux? This is one of the pieces that makes F prime development nice, is it will run on your desktop just like it will run on a Raspberry Pi or on the Ingenuity embedded Linux, which means you can test on your development station up to a certain level of fidelity before you even try to get over to the testbed. Yeah, your desktop or laptop probably doesn't have the same sensors or same backend radio, but it does have the same processing capabilities or similar, which allows you to test some of the features of software right out of the box. So, how is F prime used on the Ingenuity helicopter? To understand this piece, you need to understand the architecture at a very high level of the Ingenuity helicopter. So we had two primary deployments of F prime, Linux, and our avionics box. That is the helicopter itself. That's the piece that flies around Mars, takes pictures, wows audiences, etc. And then we have on the rover itself is a helicopter base station. This is yet another Linux and F prime deployment using the same avionics, just flattened instead of in a cube, and it's attached to the rover. It contains a mirrored radio so that the helicopter can communicate with the rover and send its data back to Earth. That way, the Ingenuity helicopter, which was designed on the order of a couple of kilograms, doesn't have to bring a big, heavy interplanetary radio to talk all the way back to Earth. So we use the rover as a communication hub to get our data back home. Now, as I said, each of these boxes is running F prime and Linux, and we can take a look at what that looks like here in this slide. The Ingenuity system design is primarily composed of a Qualcomm Snapdragon. So this is the piece that's running Linux, and it has F prime running inside. The Snapdragon is attached to some cameras. It is also attached to some back-end electronics like an FPGA, and we have a little deep bare metal microcontroller, not even running an OS, that does some of the sensor and GNC interactions. And all of that stuff is built into that cube you saw on the last slide, that is the helicopter. From a software perspective, we have the F prime application runs in user space, and we're taking advantage of those Linux user space drivers. That's another piece that makes development easy is we can grab those drivers that everybody uses in Linux and use them for our application. All of that is running on top of the Linux kernel. We did not have the RT patch, but we were using the preempt patch. And that Linux kernel contains the core drivers that are actually talking to hardware. So the user space drivers talk to the pieces in the Linux kernel that control those subsystems. That is the hardware and software architecture of the Mars helicopter. So the natural question is, how did this all work out? This here is a graph of the helicopter system. Now, you can see the various regions here, but what we're looking for is how much margin do we have in any particular phase of the mission? Because if you're getting very close to 100% or over 100%, you're going to start running into problems. So you can see here on the flight side, almost all of our processors, in fact, all of our processors here, are under 60% utilization. This is while we're in the air running visual navigation, GNC, and trying to control this helicopter, as well as talk down the radio to the rover and everything else. So that's very good. It means that we had plenty of margin when we were flying and that the helicopter was very safe. Later in the mission, this is the next thing where it says log to storage. You can see we do get a few spikes up higher in utilization. This isn't a major problem. This is when we're taking buffers out of memory and writing them to disk so that they're available for, say, downlink. At this point, we're already sitting safely on the ground. So if we do go above our safe margins of utilization of the CPU, it's okay because what can happen when you're in the ground? If you're flying, you might crash. If you're sitting on the ground, the processor might throttle a little bit and you might slow down. And then finally, you can see here in the next piece, we're doing some file compression, and then the helicopter eventually turns off at the end of this mission. Long story short, Linux running on the Qualcomm Snapdragon, running F prime, works out well. It fits well within the margins that we're looking for. And as you may have seen on the news, we had many successful flights using this architecture. So that's a quick overview of how F prime, Linux, and the Ingenuity helicopter produced a viable and successful flight mission. Before I dive into some of the lessons learned, I will pause again for questions because I believe I'm running a little bit ahead of schedule. So I have some time to take a few questions.
Do you use any hypervisors or anything in order to separate the cores?
So that is an active discussion in the post-Ingenuity era. On Ingenuity, we did not use any hypervisors. It was just the Linux kernel running a user space application. Our user space application did run as root, mostly because that helps sort out permissions and things in case we forgot to set permissions or groups or anything like that. But it was a root user running a user space application right on the kernel itself.
Quick question about the base station.
Yes.
My understanding was that someone was looking at repurposing the base station since it's got some pretty good compute on it to do something else for the Perseverance mission.
So I will note that the discussions of that have happened after I departed from this mission and moved on to the next thing. But your understanding is correct to the latest knowledge I have, which is that the base station itself, running a multi-gigahertz, multi-gigabyte system, is being used and looked at as a way to do more processing power than the traditional rover can have, because effectively, in terms of the computers on the rover, they have a little mini supercomputer on the side, which is the base station. So now that the Ingenuity helicopter is sitting stationary and the rover is continuing to do its business, they are looking at other ways to take that base station and use it for the power that it has. And we'll see some of that play out in the lessons learned in just a moment.
You said the preempt patch. There is really no preempt patch. Did you mean the preempt config?
It may be. So my understanding of the deep kernel on Linux is a little bit limited. So that bit of information I've inherited from some of the people who were working in the kernel. The key takeaway is that we weren't using the RT patch because that is what we get asked most often. But we're also not running the core standard Linux. And so if the correct way to phrase that is we are using preempt config, then I will take that back to my team and update our internal information.
Yeah, if I understand correctly, the reason why I didn't use the preempt RT patch, I asked about this when Tim came to give a talk.
Yeah.
He said that it was because the drivers that came with the Qualcomm board didn't support the preempt RT patch, because a lot of little changes you did, the preempt RT patch already solved for you. So you had to write a bunch of code on top of it to solve it because the drivers weren't supported by the preempt RT patch. That's from my understanding discussing. FYI, by the way, I'm one of the preempt RT patch developers.
Fair enough. So what you explained does mesh with my understanding. And as you've said, Tim Canham was the lead software developer on this project. And we'll get into this in the lessons learned, but the big takeaway that we had was we didn't really need it because the system was fast enough that it worked out well. And some little changes to how we architected the system allowed us to run in a mode where the traditional real-time guarantees from the operating systems we're used to using on the big flight missions, we could really work around. And we'll see that briefly in the lessons learned.
Yeah, I think the thing was priority inversion is what you had to worry about, and that's what the preempt RT patch gives you for free.
Any other questions?
Got a quick question.
Sure.
Based on your experience with Ingenuity, can you
comment on any other open source software you may or may not have used? I think Python might have been used somewhere, or I don't know,
So
or
we
Bash.
will,
You made use of Bash scripts, for example.
yes, we've used Bash scripts. We have used in extended missions, we've used Python scripts. I believe we used the system. Is that right? The system orchestrator, I think ours was predating System D, so we may have used Upstart instead. But don't quote me on that because I don't remember. It's been a few years since I've looked at that. But that is one of our lessons learned that we'll get to in just a moment. And so we've used a lot of open source technologies there. A while back, GitHub did a survey of what open source software we used on Ingenuity and then produced the Ingenuity GitHub badge. So if you're interested in the results of that survey, you can look up what that badge represents and what projects on GitHub have that badge. And if they have that badge, they were used on our project somewhere. But there is a lot of open source that's going in on Ingenuity. I should also point out we weren't the first Linux user or the first open source user on Mars. The EDL cameras, I believe, the system that lands the rover, beat us to it because they brought the rover down slightly before the helicopter was deployed.
Fair enough.
If I recall correctly, that was a ruggedized Intel, might have been an Intel Atom based system.
Oh.
Is this the EDL cameras?
Yes, EDLs. I know they used USB cameras. Yeah.
So I don't know enough about that design to speak about that. All I know is that they were running some open source software in Linux before we did by about a month.
So if you could, we started off the morning talking about the different levels of safety that you guys here at Tuesday have between human rated, non-human rated, mission support, so on and so forth. Can you share what level this system was developed to? Because it seems from what you're describing, not having the preempt RT kernel patch in place, not having you're writing stuff in Bash and Python, you're not likely not at the extreme levels of safety criticality. That maybe
Yes.
otherwise.
So I would request that we come back to this discussion after we go through the lessons learned, just so I can close out the talk. I've got like 3 more slides, and then I will answer that question. Is that all right with you?
Very good, thank you.
Excellent. Don't let me forget. I will do my best to remember. Let's dive into some of the lessons learned about the project. So Linux supports efficient development. This is one of the big boons that using Linux with F prime for Ingenuity had for us, is we could develop on commodity laptops, commodity hardware like the Raspberry Pi, and we could test a lot of our code without a proper flat sat. This means that the traditional development model of writing software, writing software, writing software, and then they build a, $500 million test bed, and then you go run on the test bed doesn't hold. You can give a Qualcomm Snapdragon or a Raspberry Pi to basically every developer you have and let them test on the hardware on day one. So that kind of availability is critical for some of the smaller scale missions that we do. Standard user space APIs allows efficient coding between projects. So the drivers that we developed to manage the Linux user space driver interactions, we have moved from the Ingenuity project to multiple follow-on projects, and they're actually available in our open source repository. That's because the user space APIs for these drivers are standard. They're documented in the kernel, and we can build it on top of them. And then finally, the big one is board features. Wi-Fi was essential for our testing. It takes a while to get a radio up and running, and the radio can't handle all of the data that you might want to see during a ground test. So our little mini portable Wi-Fi router that the Linux board would attach to ended up in a number of places like test beds and Atlo so that we could pull down data and see what the helicopter was doing and not be constrained to that environment. We still ran our tests through the constrained environment because you need to fly as you test, or test as you fly and fly as you test. However, the ability to get some ancillary data when the test went wrong was imperative to quickly getting through those tests and moving on. Next, you need to plan for robustness. At least in our case, we talked about not having the real-time patch, so we designed our software to handle some slips. As we talked about, there are some cases where you can get priority inversion. There's some places where bits and pieces run a little bit longer. And so we just designed our software to be a little bit more tolerant of the timing that we would expect running the system. And as you saw with our graph, everything worked out fine. Next, I/O. File I/O has an impact. And so one of the system design pieces that we did is we took all of the data that we collected during flight and stored it in RAM buffers until we landed on the ground. Those peaks that you saw in the performance graph when logging things to disk is when we're taking images and flight recorded data and taking them out of RAM and dumping them to disk. That way, we're not going to have a large amount of file I/O impacting us during the critical phase. You can still do this work, just schedule it outside that critical piece. And then finally, the abrupt power offs can cause file corruption. The Ingenuity helicopter, it basically had a hardware timeout that would just kill the power to the processor. And that isn't necessarily great for all of the time. So what we did is we made sure that the kernel and the golden software images, that's the piece that we run, were all on a read-only partition. That way, that partition will be the same each time we boot up, and any given run of the operating system and software shouldn't change that. And in this way, we at least had confidence that that initial read-only partition was ready to go the next time we hit the power switch. And then finally, this is some of the pieces you all were pointing at, is it's Linux. Remember that piece. So Shell and Android debugger were available for our development and testing. So we got in there. We did run bash scripts. We did have the Android debugger to check out our hardware and start looking around. We also used system calls to extend mission functionality. So we have a component called the file manager that could dispatch system calls. And that allowed us to run user space commands like bzip, md5sum, ls, python, remove, bash, all of these things. We were able to be flexible as an operating mission because we had the ability to use these other pieces. For example, there was a fairly critical bug in our file listing capability built into the software. If it hit a large file, it would hang long enough to trip our watchdog and cause a flight software reset. So we learned really quickly, don't run ls on the helicopter. We need to fix that on the ground and make sure that it's better for the next mission. But we still needed to list files. If you have a system and access to the console, you can just run ls and suddenly you have that file listing capability from Linux user space applications. Some of you started poking at bash and python. Python wasn't used for the primary mission, but as we got more and more and more requirements, moving from a prove you can fly to an operational demo to a science scout, Python became critical because uploading Python scripts was a lot easier than uploading complete changes to the flight software. So even if these things aren't intended for the primary mission, having them available and at your disposal makes extended missions and changes to your mission objectives much easier to accomplish. So that is my talk. Looks like I have just a minute for the questions. So let me get back to the question on what grade we are. So my understanding of the various levels of software safety is the class system. So class A is human space flight. Class B is roughly one of JPL's big mission rovers. Class C, I'm not sure what it is, but Class D is CubeSats and other missions of that like. The Ingenuity helicopter was designed to be Class D. And so we did a lot of engineering expecting it to be Class D because it started as a research concept. When we got baselined with the rover is a Class B mission. And so the interfaces with the rover, that is where the Qualcomm Snapdragon talks to the radio and then to the base station, which then talks to the rover, those needed to be engineered to Class B standards because they had to match with the rover. But the remaining flight system was Class D. So you're right, this isn't the highest grade of safety application. However, in future missions, we are looking at how can we improve the Ingenuity design such that we can migrate to a higher level, more like Class B with the rovers, because we're researching other helicopters that can be their own standalone robotic mission or supports to other missions that have that Class B standard, and we need to live up to them. And one of the things that we do have on our list to investigate is the RT patch. I think I'm out of time for questions.
Just saying, the RT patch is no longer a patch, it's actually upstream now.
Oh, excellent.
Last month.
Well, what version of kernel are you running on?
Or do you plan to run?
Yeah,
I can tell you that.
So I don't know off the top of my head.
Okay.
Future missions will decide based on when they solidify their choice of hardware platform and vendor, because many of the platforms we've looked at get a operating system from the vendor itself. So Qualcomm supplied the Linux distribution that we ran on Ingenuity. Unfortunately, I don't have on the top of my head which version Ingenuity was. I want to say 4.15, but don't quote me on that because it's not something I've looked into for a few years.
Okay, well, I think, again, thank you very much, and we need to get to our next speaker.
Absolutely. Thank you all. You can find us on GitHub at NASA F
There is a
Prime.
question, there's
Oh.
a question in the chat, and so
Oh.
if you could answer the question in the chat afterwards, and stop
Yes.
sharing, move on to the next speaker. Ivan, you're up.